Hi, in the previous session, we have already discussed about the different type of bending and different cross section. How this cross section, forces vary with respect to different kind of the type of forces if you apply on that, and its denotation, notation on the different element. And with respect to a different element, we are able to find out the Moho circle, and from that we can find out the principal stresses, strain. And uh, in this lecture, we are going to start with the basic of the shear force and bending moment diagram, and also going for the few example as well with respect to that. Before that, we have to check with a few basic fundamental that we already have discussed, but it's a basic, and it is required to understand before going to this shear force and bending moment diagram. So we already have seen that bending is nothing but it denoted by two notation, that positive notation and negative notation. Positive is for sagging moment, which can you see in the left side of that PDF, which is denoted by this diagram. So this is nothing but your notation, and in this condition sagging moment, there is a compression stresses and compression vessels taking place at the top portion, and the bottom portion which shows the tensile stresses in the, and upper stresses compressive stresses. But this compressive and tensile stresses vary with respect to from top to the bottom, and at some away from this two top section, it has a one neutral axis section. So in that section there is no shear, there will be no force of tension and compression. So we used to call it as a neutral axis, and the bending stresses and any kind of stresses, then there will be no extraction and the compression, which is nothing but the contraction and expansion of that cross section is not taking place. It will remain all after bending. Also, the length will be remain same of this axis. And similarly for the hogging movement, which is just right to that diagram as we've seen in this diagram. So we have taken the moment, which is if it is clockwise moment, we take as positive, and if it is negative moment, that we take as negative moment. It's totally based on your choice, but you should be keep in mind that you have to follow the entire section, the similar notation for that, because it will create a little bit confusion while solving this kind of example. In pure bending condition, in which only bending moment is applied, and while applying the bending moment, there will be no axial load is taking place, there will be no axial expansion, that extension and compression. There will be no shear forces, because there is no shear transfer force applied to that cross section. There will be no twisting moment. So testing this kind of three kind of the forces is zero in this condition in pure bending. And they used to ask in some condition, this is the base peculiar condition with respect to that, this from the neutral axis, from the y distance, there are different layer, and it varies their extension. If you try to compress or bend any different manner, if you move away from the in the upper from the neutral axis to the top portion of that cross section, the extension is going to be reduced, and at the top section it is almost reduced, that like more extension will be there. And in the bottom section, if it is a tensile stress, then the more less stress at the nearer to that neutral axis. And as you move away from that neutral axis toward the bottom portion of that cross section, the extension of that portion is going to vary. And sometimes they used to find out, you ask to find out the the elongation of that particular section, or that layer from neutral axis. So at that point you need to find out the extension as well as the shear stresses bending moment. and many other things you can find out. And here is another formula, and we used to denote as a y, that the cross section we have taken as a xx cross section, from which we have to find out the stresses, strain, and bending moment. This formula is very basic, and you are familiar with this, which is nothing but moment of inertia, moment divided by moment of inertia equal to the bending stress divided by the y-axis distance from the neutral axis of that cross section, and E is the Young modulus divided by R is the radius. After bending that cross section, the radius is formed, and the neutral axis, which is near to the which is on the point of the center, is on the neutral axis. So from this we can find a different notation and a different cross section, because this is very basic formula from we can denote many notations. So the first is the bending stresses, and bending stresses we can be which will be equal to, if you want to find out the bending stresses at that particular section, which will be, if you multiply with respect y into the other form in other direction, so it will become m y by divided by r, and I is the entire cross section moment of inertia of that section. So this is how we are going to see. Yeah, this formula is very helpful in the upcoming session, but only this is a little bit introduction for these formulas. Now we move to the other basic fundamental, and in this which we are applying the pure axial stresses. So if it is the pure axial stresses, there would be no shear, because we know there is no transfer forces. There will be no bending moment diagram, because there is no any kind of bending stresses will be there, and twisting moment also will be not there. Only the axial loading will be applied, and in this condition, a rectangle moment we can see as a shear force diagram, and the bending moment diagram will be zero. So it is denoted by force upon area and change in length PL by A. As we seen, the different cross section is there, and different cross section shows the different the different orientation for the shear force and bending moment diagram. But it shows in this PDF that does not depend on the cross section of that material and the shape of that cross section, because as you see in the left side, shear force loading diagram, which is independent of shape and cross section of that material. So first, which is cantilever beam, and it's like single rod. But in the second diagram, it shows that it's a compound beam. It's a compound beam, and it's cantilever beam. So in both the conditions, shear force diagram as well as bending moment diagram, both are the same. So it is not depend on their cross section as well as the type of material they were used. And just right to that diagram, it's a different kind of loading which is applied on the rod, and it's cantilever kind of thing. So the first notation, which is in the rectangular form, and which is denoted the axial forces, and when you apply the forces inside the cross section, the axial forces will be distributed in entire cross section will be equal. So it is denoted by the arrow direction. The length of that arrow will be same for the entire cross section from the top to the bottom. So it's denote that the stresses in entire cross section will remain same. Now we move to the bending stresses, and in the bending stresses, we know that at the top cross section, and in the previous axial tension and compression, if it is tensile stresses, then entire cross section is in tensile stress. If it is compressive stresses, then it is entire cross section will be in the compressive stress. But in the bending stresses, the top cross section, it depends on the sagging and hogging moment. We take as a sagging moment, in which the top portion will be in the compressive stresses and the bottom portion is in the negative stresses. And these two cross section, that tensile and compression, which were separated by the neutral axis as we have drawn. So it is it is cross at the neutral axis. So the above portion we can see the compressive stresses, and the bottom portion we can see as the and it is equal amount of stresses which is present here. This is compressive. It shows that compressive and negative stresses are equal, but it is opposite in nature. Now we see that eccentric kind of forces is there, so in which the axial forces is there, but it equal to be the bending stresses. And in this condition, the top portion will be at tremendous compressive stresses, or it might be in tensile stresses, and it will be zero at the bottom most that cross section. As we move from the other section to other section, in which the bending stresses is higher compared to the axial stresses. So due to that, what will happen? Due to that, the neutral axis will be shifted toward the bottom side of that neutral axis, because the bending in the bending session, the most tensile stresses will be developed at the top most section, and the compressive stresses will be at the bottom section. So the combined, if these two pay effect get combined together, that neutral axis is transferred towards the bottom section, bottom most section of that. And any other another condition, if the axial stresses is more than the bending stresses, which shows that the entire cross section we take as a positive, and the neutral axis will be meet at the outside of that cross section. And I have taken a few small example in which I have differentiate this kind of notation in different manner. The first condition I have take in which I have taken the axial, this axial stresses is equal to bending stresses, then axial stresses in the greater than bending stresses, and in third case, in which axial stresses is less than the bending stresses. And for this condition, I have taken with the stresses at the top of that cross section, and bottom layer of that cross section. So first, in condition, the both axial and bending stresses will be equal. So in that condition, as you see in the third notation from the leftmost of that bar. So in this condition, the first portion, which shows that the axial plus bending stresses give the positive stresses, and in the bottom stresses it meet on the bottom section. So it will be a zero on that bottom cross section. So that's why the stresses at the bottom will be zero, because both are equal. And in second condition, when the stresses are the axial stress is higher, in that condition, as you can see that in the last diagram on that on that bar. So in that bar, at the top section it is positive, and as well as in the bottom section it is also shows that positive and it meet an outside to that cross section. But as we move from the second to third case, in which the bending stresses is higher than the axial stresses, so the neutral axis will be remain in the cross section, and due to that, the topmost portion it will cover the positive, but due to that bending stresses is higher, so it will make that bottom section as a negative, which that shows nothing but that if top of that cross section is in the tensile force, the bottom is in the compressive inertia. Here is the few properties of a ductile and brittle material. So this kind of properties are very important to understand the material behavior with respect to tensile and compressive stresses and their properties. Uh, yeah, I have taken the ductile material, which is I have taken the comparison between the yield compressive stresses, yield tensile stresses, and yield shear stresses. In these three conditions, I have compared with in this kind of material, which is more efficient in which condition. whether it will be good at the compressive stresses, it will be tensile stresses and the yield stresses. As we know, if you apply the tensile stresses on the ductile materials, so what will happen? It will get elongated, and after that, it will reach up to ultimate point, and after that, start breaking. And in the compressive stated, what will happen in its same diagram will happen in that stress and strain diagram, but it is in the negative direction. But if it is apply the shear stresses, so shear stresses is somewhat which we are trying to twist that moment, and in that condition it is not able to sustain that much force. So same material, if you apply three kind of these forces, so it will be the tactile it will gain it will sustain up to more compressive stresses compared to the tensile stresses, and the less efficient is for the shear stresses. And in different theories, they used to find out the different notation for to compare this. And first is if you want to find out the yield shear stresses, which will be equal to the yield stresses divided by 2 in the maximum shear stress theory, and yield tensile stress divided by root 3 is maximum destruction theory. Its own Mises 3, and it's also different name is given. We will see in that respective diagram. So similar condition, if you checked for the brittle material has a property which is go up to entire directly to the ultimate tensile stresses. It's not show any kind of elongation and deformation inside that material, and it suddenly get break. So in that condition, it is also shows the similar pattern. It will absorb more compressive stresses than the tensile stresses. But in this condition, the brittle material is good in the shear stresses. So we mostly seen that cast iron. Cast iron is mostly used for this shaft kind of material because it is good to absorb the shear stresses. This is shear kind of stresses, and compared to tensile stresses, and the brittle material, as we know, it's very poor in the tensile stresses because it will directly it suddenly break. So mostly they use for in the compressive and the shear stresses, and the more best example for the compressive stresses is the die. So mostly dye is used for the brittle material, and there is a lot used these days because, and mostly for the machineries, it has a very damping. It has a good damping capacity in a brittle material. So that's why used for the machinery beds, and the most the shafts is used to made from this because they were never use this kind of uh, ductile material for this kind of shaft because it get deformed, and it is not able to transfer the power. So it shows that ultimate compressive stresses is much higher than the ultimate. It can sustain the ultimate compressive strain in the very large compared to the ultimate tensile stresses. So we never use this brittle material in the tensile force condition. And if you find out, so it is capable of sustaining the stresses which will be 3 to 4 times more than the tensile stresses. But the deformation in the cast iron will be higher compared to the elastic deformation in the MS steel. So it has a little confusion because we know that the elongation of my steel is more compared to the cast iron because it's a ductile material. But the deformation, it's a word is a demo in elastic deformation. Elastic deformation, the cast iron will deform more compared to the deformation in the mild steel. But if you take for the total deformation, in which the mild steel will be deformed in a very large manner compared to the cast iron. So, if it is asked within elastic limit, so in that condition, the cast iron will be deformed in a greater amount compared to the mild steel. And if it is asked the total amount of deformation, so in that condition, the mild steel is going to be deformed in the large quantity comparative to the cast iron. Now we move to the shear force and bending diagram. So shear force and bending diagram, there are different kind of load and different kind of beam cross section. Uh, given and already we have discussed the different type of beams and the loads which is acting on that beam. So we already have seen. So we going to find out how to find out the load of that unknown load on that beam with respect to that particular kind of load. And here I have taken one simple example where I have denoted the all kind of the load which is applied on the this kind of application. So first I have taken the simple supported beam and the first load which is acting in W. So, which is the notation for this is the notation which is W, and it's called as the point load on that beam. Now we move to the second load, so which is act as a movement in the anti-clockwise direction. So it is a point load, which is its moment. It's a point moment acting on that beam. uh, Moment and there is a little confusion between the moment and the couple, but you should keep in mind the both are the different thing. My The moment has a different notation and the couple has a different different meaning. Couple is nothing but equal and opposite magnitude, equal amount of magnitude act in the different direction, which is separated by some distance. So that is called as a couple, and moment is the force applied at particular distance, multiplication in between them. So this is the basic difference, and this third notation is this kind of force is also going to act on that in this application. Now we move to the uniformly distributed load, in which the entire span of that cross section, which is uniformly uh, load is distributed on the entire span, and it can be denoted in a different manner. Firstly, it is denoted by this, and secondly, also it can be denoted by in such a manner. And there is another kind of load is uniformly, as we see now, it's uniformly distributed load. Now we can see the uniformly varying load. The denotation is the different variation. Only the orientation can be changed, and in which this can be the notation for the uniformly varying load. And just try to that notation. It is small moment which is uniformly distributed on that load, that bar. So it's called a uniformly varying moment. If it is varying, it's if there is a moment, it has a different magnitude. We used to call it uniformly varying moment. But if it is, the moment will be remain same and direction will be same. So it is uniform moment on the entire span. Now we move for the how to calculate the value for unknown value for the simple beam, and with respect to the different kind of notation. For the point load, we know not to think about, and also moment and couple. Only only we face the problem in uniformly distributed load and non-uniform distributed load. The first we go for the uniformly distributed load, which is the magnitude of that load multiplied by the entire span, and the acting at the equal distance from the both end, which is L by 2 L by 2. So This is how we are going to this is going to, and with respect to some of vertical moment, some of the horizontal moment, some of the some of the vertical forces, some of the horizontal forces, uh, and some of the moment. With respect to these three equation, we can find out the two unknown forces. Now we move to the second diamond, which is uniformly varying forces. So in which the magnitude is nothing but W, and uh, the notation, the total magnitude of entire force is going to be act at the single point notation, which will be the magnitude will be equal to half of weight into length of the entire span. So this is going to be the magnitude of that forces, and the point of acting, which is varying where the load is low. From that point to 2L by 3 portion of the length, at that moment it going to act, and from the bigger end it is from the L by 3 notation. And this kind of loading is also useful in the fluid dynamics as well, because in that kind of notation, because the pressure of the water is varying with from the top section of the top surface of that water to the bottom surface of water, it's varying uniformly. So this kind of structure is there, and uh, this will be very helpful to for solve the problem. And this is the very peculiar form of the example, which mostly use in the direct notation, because it's kind of ideal example. So they were never used to give in the combined form. If they want to ask this kind of equation, they will ask separate question on this kind of structure. So it's a simply supported, and it's very like semicircular kind of load will be there. It's uniformly varying. So you can find out with respect to integration and different manner, but I am going to find out the total magnitude is going to be act on that will be which will be 2 by 3 times of weight into length of that cross section. And just keep in mind that most of time they used to play with this unit of that two quantities, length as well as the weight. So just just take a pause and just verify whether that unit what they have given, and what is they were asked. And if you want to find out the RA and RB value, that is nothing but the unknown forces at the both end of that structure. So that can be find out with respect to which will be equally distributed on the both end. So the entire magnitude is nothing but 2 by 3 WL divided by 2, and that equation will become the WL divided by 1 by 3 W into L. So you should keep in mind, and this is how we are going to see this example for. And now we move to the another section. So see there different kind of relation in between this shear force load and the bending moment, because with respect to once you find out the load, you can find out the shear force, and from the shear force diagram you can find out the bending moment diagram. And the relation between these two is that the entire area under the loading diagram, which will be equal to the shear force which is acting on that diagram or acting on the structure. And the area under shear force diagram, which is nothing but the moment which is acting on the structure, and it can be denoted as the rate of change of moment with respect to the span, which is x I have taken. So rate of change of or you can say a differentiation dm, this is nothing but m is nothing but the moment, and the variation of the differentiation of m with respect to x, which will be give you shear force. And if you take the differentiation for the shear force, you will get the load acting on that cross section. And as we know that if you want to find out the load from the diagram, so it can be denoted as well. The W is the load you can find out with respect to the derivative, first derivative of the shear force. And if you want to find out from the load from the moment diagram, so you can take the double derivative of that moment with respect to that x value. So in this way you can find out your load from that diagram. And the note this differentiation with respect to the bending moment, which also called as the slope of the shear force. Shear force which will be the slope of the bending moment diagram, and the load will be equal to the slope of your shear force diagram. And the angle of that diagram will be always greater than 1 degree of the shear force diagram, which shows that shear force diagram will be the angle which will be greater than 1 degree from the loading diagram, and the bending moment diagram, which in which case the angle will be 1 degree greater than the shear force diagram. As also we can see in this the following notation for the different diagram. So how it's going to be changed when the bending moment is going to be from maximum condition to minimum condition. It changed their sign from the, it's like a positive sign, it's a clockwise direction. So it goes to the negative sign, it shows the negative, and it's passing through the center line. So that center line also, that when the bending moment diagram is cross that neutral axis, there the magnitude of that bending moment equal to be zero, which that point we used to call it as contraflexure point. And this is the most important point to ask a question, because at that point bending moment is going to be zero, and with respect to that you can find out the shear force as well as the distance from the different structure where the shear force is the bending stresses will be zero. So at that moment you can easily find out the shear force. So this point is very much important to be remember, because most of time they used to ask question on this as well. And as you move from this diagram to the different kind of notation, and how we used to draw this kind of diagram, which will be if you remember this kind of a notation, so it is going to be very easy to remember. And there is a there might some question they used to ask directly. They will give you who the surface diagram, and they used to ask you find the what will be the bending moment diagram for this particular surface diagram. And sometimes they used to give the bending moment diagram, and they used to find out the surface diagram. So in that condition, this kind of notation is very much important to remember, and which is nothing but show your the behavior and the variation of your shear force and bending diagram with respect to this different kind of load. So first I'm going to take with a point load. In the point load, if you go with the shear force diagram, so it will be in the rectangular form, horizontal uniform kind of shear force diagram will be given. So in this condition, it will be show the horizontal diagram, like structure kind of thing. Uh, so this kind of diagram you can see on the shear force diagram. And if you see this kind of shear force diagram, you if you want to find out for the bending this point load, the bending moment diagram, it will be in the inclined line. So you see that when you move for the bend shear force diagram, if you want to draw uh, the the bending moment diagram, so the point load and the formed load, you now need to draw a bending moment diagram. It must be 1 degree greater than the load diagram. So as a above point, it will be clear from this point as well. And as you move from the point load to uniformly distributed load, so uniformly distributed load. in which a shear force diagram will be equal to the inclined line, as we seen for it was for a point load in a bending moment diagram, but the same kind of notation will become for the shear force diagram in the inclined. So here 1 degree of notation is going to be increased, and in this condition, if you if the shear force diagram is in inclined line, it shows the inclined line. So definitely the notation for the same cross section in a bending moment diagram, it will be a square parabola for that cross section. And as you move for the uniformly distributed load, as we see that in the uniformly distributed load, that bending moment diagram shows that the second a square parabola for that bending moment diagram. So same thing is used for the shear force diagram for a uniformly distributed, uniformly varying load condition. So the same second parabola, square parabola, is going to be used for the shear force diagram. And once you see the square parabola in the shear force diagram, you should remember that the bending moment diagram for this load is going to be the cubic parabola. And from that you can directly come to the parabolic load. So in the parabolic load, in which the shear force diagram you get in the form of cubic parabola. And if you find out that the shear force nature of the cubic parabola is it's the shear force diagram is cubic parabola, then the bending moment of that diagram is going to be the parabola, 4 degree parabola. And the notation of 2 degree, 3 degree, this is the notation of their curvature with respect to the previous, and it's a 2 degree of parabola, which will be the slope is very less compared to the 3 degree parabola and compared to the 4 degree parabola. So this is how you're going to remember this entire portion. So it will be very helpful to solve this kind of example, and identify the structure of your shear force diagram and bending moment diagram. And with respect to that, if they used to give some bending moment diagram or shear force diagram, and you find out the loading diagram, so this is how you can uh, imagine, and you can guess whether in what kind of structure, which kind of force you're going to be apply. And in another condition where bending moment and couple is going to act, there is no shear force, as we know, in the bending moment and the couple. So in that condition, shear force diagram is going to be zero. And where shear force diagram is zero, in the and in which the only bending is there in the bending moment and in the kibble. So it will give a vertical step in that, as we seen for the band load in the rectangle form. Same kind of notation give in the entire cross section for the pure bending moment and the couple kind of stresses. So this kind of notation is given. And as we know, once again you have to remember the few point which will be very helpful for to remember. And that is nothing but when you see the sudden variation between the shear force and bending moment diagram. So, in the bending moment diagram, there is a sudden change. That is, the previously the magnitude was positive. Now the magnitude is going to be negative, and this is only happen in the bending moment diagram due to the couple and the moment. You should keep in this mind. This point is very very important. And in shear force diagram, the change in magnitude due to the point load. Only point load can change the magnitude from positive to negative. And with respect to this 2 point, you can check whether the contraflexure is going to be take place in which area, and you can directly go to the cross section and you can find out your answer. Now we move to the another section is nothing but the internal hinge. So internal hinge is nothing but the one kind of connection between two links. So which is nothing but like two links which is connected by the nut and bolt kind of cross section. But in this condition, so in this condition, there will be no a movement is going to be transferred through that link. As we see, there is no moment will be present in the nut and bolt kind of cross section. Once it's going to fix, it will be fixed, but it can be able to transfer the transfer load as well as axial load. In this condition, mostly they used to ask question on this, because most, if you know the concept behind of this hinge, so in hinge, just keep in mind, there is no moment transfer. If one end is going to be moment will be there, it will not transfer to the other end, crossing that hinge point. But when there is axial stresses or the transfer load is acting on that one end, it can be transferred to the other section. So this is the best example. This is best things to remember. And from this 3 point 2 3 point, you can go directly to the example. And here I have taken a little bit complicated example, and which will be good enough to understand. And from that understanding, you can solve the small and few example. So first, I'm going to take a simply supported beam, which will be around 6 meters span, and in both end, it is loaded by uniformly distributed load. At one side, left side, it is loaded by 5 kilonewton per meter load, and another end it will be 2 kilonewton per meter load, and it's for the 2 meter each. In this condition, if you draw the shear first, the free body diagrams already have drawn, and already have find out the value for the unknown forces which is acting at the both end at A and B. I have denoted at the A end it is acting 9 kilonewton, and at B section it is 5 kilonewton. And mostly this kind of the unknown value is not given, so you have to find out this value by drawing the free body diagram for entire cross section. And after that, you can proceed with the shear force diagram and bending moment diagram. So first we go for the shear force diagram as usual. So first, as we know, at the A condition, we move from the left to the right of the cross section, which is nothing, A to C, C to D, and D to A, which will be divided into three cross section. So first, the force at the uh, A section, we take at the vertical moment is positive, and downward force is going to be negative. So here the force at the end is 9 kilonewton, and that force is positive force, which is acting upward direction. So we take 9 kilonewton for distance from the horizontal axis, which is just down, which is just denoted in the downward direction to the 9. Uh, so in this condition, we know we have to find out because we know, as we see that if it is point low, then shear force diagram will be horizontal, then the bending moment diagram is going to be inclined. But in uniformly distributed load, there will be inclination in the shear force diagram. So there is a chances it will cross that neutral axis, or it might not cross the neutral axis. So you have to find out whether it will be cross that neutral axis or not. If the value of the forces at the C point is going to be negative, so definitely there is a change in magnitude which is going to be negative. And in this condition, you can find out, the moment, you have to calculate the moment, which is nothing but uh, which is the force at force in the x direction, in the vertical direction. So we have taken the force in the vertical direction is 9x, and uh, from the that A point, we take x distance, and that x distance where we have to find out the downward force, which is nothing but the uniformly distributed load, which is 5 newton kilonewton per meter, and multiply by that x. So it will give the entire forces. And if you put the value in this cross section x equal to 0, you will give the value the force at A equal to be 9. And if you put uh, the x value is equal to be 2, which is nothing but the force at C section. So it will give the value with 5 minus 10, 9 minus 10 equal to minus 1. So definitely it's going to be cross the neutral axis, and where the point where that point is going to be crossed. So we know that definitely it's going to be changed over there. So if you want to find out the reasons where it cross from what distance from the A end it cross the neutral axis. So you take equal to be 0, 9 minus 5x equal to be 0, where the shear force is going to be 0, because at that point it's going to be cross the neutral axis, and the neutral axis on which the shear force is going to be 0. So you take 9 minus 5x equal to be 0. If you find out the value, it will give 1.x, so which is nothing but from the A moment, from the A point, the zero shear force is at 1.8 meter away from that point. Now we want to move from the A C point to D point. There is no need to find out, because already we know that if there is no shear forces, it will the entire forces the force will remain constant. And at this moment, the force at C point, it will be minus 1 kilonewton. So it will be remains constant at till the D moment. So you can you can also calculate with respect to same value. If you put the value equal to 2, so it will give the same value as well at the C, F and D, where you get constant forces. And now you move to the B to D, that uh, uh, D to B section. So where you have to be conscious that the equation is going to be nothing but you can directly go by the values as well as the equation. But if you go with the equation, it will be more easier to understand, and there is less chances of making mistakes. So here is the force in the y direction is nothing but 9 in the vertical direction, as we know. And the force is which is created by uniformly distributed load at 5 section, 5 newton kilonewton meter for the 2 newton 2 meter. So it will become 2 into 5 minus uh, this force is which is nothing but 2 kilonewton per meter multiplied by the cross this length. And here this cross section we take as a x, we know already. And from the wherever we go move around from the ace cross section, we take as a x value for x length, and from the x length we minus that from 4. And this is give the value that this is the equation for the section for B and D. So if you put value x equal to 4, you will get the magnitude for FD forces equal to minus 1. And if you put the value for x is 6, so you will get the magnitude of the force is minus 5. And with respect to minus 1 to minus 5, if you draw the line for shear force, which will be for uniformly distributed, it's in the incline line, and there will be no shear forces. It will be the constant, as we see how this above notation of different the curvature is going to be drawn for the different load is going to be help for you to draw. And understanding this kind of equation will be very easy and to find out. Now the below diagram you take as a notation, and I will explain afterward. So if the uniformly distributed load, we know that the shear force diagram is inclined line, so then definitely there will be square parabola for the bending moment diagram. So you can see it will be vary in the parabolical form from the for the 2 meter cross section. After that we know that there will be no shear forces, and it will be point load kind of condition will be there. So only vary in the incline bending moment diagram. As we see in the point load, it is horizontal diagram, and for the shear force diagram, but it for the bending moment diagram, it's going to be incline line. So we have draw incline line, and once again we have to if we have seen that the shear force diagram, the uniform distributed load for in this is move from the -1 to -5, which is incline line. So we have to draw a second parabola from -1 to 5, which is at the right portion of that structure is the second parabola. So this is how we are going to check, and in this condition also we are going to find out the different different equation when you move from the left portion to right portion, and with respect to that, if you try if you adding the value of x, so you will get the different moment at that particular location. So as we know, as we move from the A to C section, and we have taken the random distance of around this uniformly distributed load, it's x. It is not a particular location, it's any random location. So the force, the moment is going to be at particular that point will be 9 into x, and the force is going to be applied, the force magnitude will be uh, we know 5 into x is going to be there, but due to this the forces that this distance x is going to be divided into two cross section, x by 2 and x by 2. That's why we have to multiply the x by 2 to the 5x, so it will become 5x x square by 2. This is going to be the equation for the cross section of A and C. So here, if you put the value of 0 for the entire span, so the moment at both the A section, it is going to be 0, and all the time, and each and every diagram you can see the moment at the both end will become 0. So here you get moment at A portion is A point is equal to 0, and if you put value, if you move from the A portion to C portion, so in the C portion the distance is equal to 2, and if you put the value 2, so there will be the moment 8. So as we know, it move from the 2, but where is the contrafaction is there? At that point, it's the moment will be maximum. As we know, the shear force, where shear force is going to be 0, the moment at that point is going to be high, and where the moment is going to be 0, at that point shear force is going to be very high. So in this condition, it shows that MC that the moment at 8 at x equal to 2, 8, it's 8 kilonewton meter, but it is not the highest moment. So it hold the highest moment at 1.8 distance from the A point. So if you put the value x equal to 1.8, you will get the actual maximum the moment value, and which shows that where you can take the shear force diagram. Where for maximum bending moment, as you know, the shear force, where the shear force is going to be 0, the rate of change of bending moment equal to be uh, uh, 0. So there the shear force is going to be maximum. So in this condition, the moment is going to be 0. So here I have taken, if you differentiate this equation with respect to x, so it will become 9 minus 5. 5 is 2 to get cancel each other on 5x. So this is going to be the equation. So if you find out the value, so you will get 8.1 1 Newton meter, and directly if you this is your for your x value, you can find out the x distance uh, from this equation as well. If you already have find out the x distance from the shear force equation, as well as similarly you can find out this x distance from the this equation. So where the point is going to be, as we know that where the shear force is going to be 0, and here the bending moment is going to be 0. So in this condition, the differentiation is equal to be 0. So this is how you get x equal to 1.5. and if you put 1.5 in the above equation, mx, so you will get the maximum bending moment is equal to 8.1, which is higher than 8 kilonewton meter. So if they ask you what is the maximum bending moment in the entire cross section, so this is where the shear force change the bending moment, shear force cross the neutral axis, where the shear force is going to be zero. There you have to find out the bending moment. At that point you will get the maximum bending moment. And now we move for the CD cross section. So CD cross section, in which the entire cross section will be remain same. So only thing is change where in the CD cross section there will be no forces. So there is no addition extra force in this equation. Only thing is change that is when 9 Newton meter multiplied by x minus the force is 10. This is the 5 kilonewton meter of force divided by in multiply by 2, which will come equal to 10 newton meter, and the span is nothing but x minus 2. We already have taken that wherever you take the cross section, so we take at that distance as x. So 9x is going to be there, so because we have taken, and from that x equal to x distance is there for the 8 point, so 9x. And when this magnitude will be there, so the magnitude of entire that uniformly distributed, which is we're going to be 5 into 2 equal to 10. And the intermediate section from x is going to be no, that section is going to be x minus 2 value. So this is how this forces, this equation is going to be represent. And at that moment where you find out the x value equal to be 0, so there you already find out the value in newton meter, you can re-verify, so you will get the same answer. And if you put the value x equal to 4 meter, so you will get the moment at that point equal to 6 kilonewton meter. And at the last moment, if you take the cross section for the BD moment, so the equation is going to be similar from that section is going to be 9x minus 10 into x minus 1 in bracket minus 2 in bracket 2 minus x minus 4, and it's square divided by 2. And why it is so, because already we have discussed that x minus 4 you have to take, and the half portion of that uniformly distributed, which we have to multiply, which is nothing but x by 2 divided by 2. So this is how it become like this. And with respect to x, if you get the value of 6, so this is equation will be correct. And if you take the x value is equal to 6, then definitely there is a change, there is the bending moment equal to be 0. There is another example as well, but it will take much time, and it is quite simple comparative to previous example. So you can understood. So understood as well as I'm going to discuss in the next lecture, because it's going to be a very large video if I cover the same in this lecture as well. Also, see you in the next lecture.